To begin with, we identified a new challenge, which is the distribution and storage of the COVID-19 vaccines in rural areas. These places undergo specific conditions that make it a lot harder for this to take place. In the case of Colombia, the Amazonas Department faces most of these conditions. To evaluate the best alternatives, we also took into consideration the different vaccines that were developed in the past year, Pfizer being the most demanding one in terms of storage temperature.
About the target, we selected this place because we want to help this region that is very affected by the COVID-19 due to the closeness with Brazil, additionally to the limited economic and electrical resources and in the situation in which they live.
We determined the requirements in two phases. In the first one, we divided it into criteria and restrictions based on the target audience and the needs identified. In the second phase, we compiled both the criteria and the restrictions in order to make 7 criteria: the refrigeration system, the damping, the weight, the size, the cost of raw material, the time without energy source, and manufacturability. We will get into detail later. For concept development, we divided into 4 subgroups, which would take the information that we already had with the criteria, make prototypes, develop models, and then share them with the group in order to compare different kinds of systems.
The first alternative is to design a small refrigerator based on the system developed by Churchill, which take advantage of the fact that water varies its density with temperature, reaching a maximum at 4 Celsius degrees. So the water will flow around the vaccine compartment, keeping it at this temperature. The first estimates suggest that to achieve a 24-hour autonomy, there must be a minimum of 8.14 kilograms of ice and a 4 cm thick thermal insulator.
The purpose of this alternative is that it works as a fridge due to the fact that the principle used is the closed Carnot cycle, as you can see in the images on the right. It works through 4 essential components: compressor, condenser, expansion valve, and evaporator. This entire system is powered by a 30-watt solar panel, which charges the battery and allows it to work without the need for an external source. The dimension of the fridge allows to have the system on the right side and the vaccine compartment on the left side, for which it is designed to fit around 9,000 doses.
In alternative number 3, we designed a heat isolating system composed of 4 isolating chambers and vials chamber at the center. Our prototype has a cylindrical shape. We based our calculations assuming vials contained water, and we calculated our average rate of heat transfer, where A is the number of boxes and T is the time required. Finally, we made a heat transfer model under some considerations.
With these parameters, we were able to create an analysis of the thermal conductivity in relation to the thickness of the isolating chambers. Some additional considerations that appeared with this analysis were that the best isolating material would be a polymer, and the insulating chamber would be filled with air.
The solution consists of a portable fridge that will use 3 molds of organic solution phase-changing materials of the type A2. Each mold could keep 400 vaccines, and the system will keep the vaccines between a temperature of 2 to 8 degrees in a period of time of 49 hours.
For the evaluation, we had 7 different criteria with their percentages. We used a rating system for each criteria from 4 to 1, 4 being the best, 1 being the worst, and the final score of each prototype was calculated as the sum of each criteria with their respective percentages. If all alternatives have the same performance, we gave them a score of 2.5 for a given criteria.
We evaluated each of the alternatives with the criteria mentioned beforehand, and the summary is on the table that you can see on the screen. The final results were, for the first alternative, 2.90, for the second, 2.55, for the third, 2.30, and for the fourth, 3.25. For the final concept, we decided on the combination and integration of the third and fourth alternatives, resulting in a system based on insulation chambers and PCM refrigeration. We concluded that the PCM would be a great complement to the insulation chambers and would allow the temperature to be maintained in the range that we want for a much longer time than we thought. Also, we concluded that the geometry that we could make with this mix would be highly accurate and highly comfortable for the transportation, and it would also be a cost-effective alternative. The two subsystems in which we would be working on would be the insulation and the refrigeration. In this first sprint, MediMec was able to find viable and diverse solutions, and we managed to build a healthy team dynamic. With the decision that we made, we need to take some things into account for the future work. The first one being the geometry of the new system, the way in which the PCM will be manipulated. We need to develop high-resolution prototypes specifically for damping, system temperature variations when the system is opened, heat transfer models with convection and radiation, manufacturability internationally and nationally available to us, and we need to find a more precise budget. Thank you very much.